problem was just a combination of those unsteady oscillating plate and the interface conditions. If you figured out how to implement the interface conditions properly, then that problem wasn't difficult. And then the third problem was a little bit daunting to look at, but if you followed the procedure of Stokes flow past a sphere, it was quite simple. It was exactly the same procedure, just whatever functions you get, they will be different. Of course, I cannot give the same problems in the exam which I have covered in the course, but I can give similar problems at least, and these were all similar problems. So, in any case, let us resume with our discussion on lubrication theory. So, in our last lecture, we were looking at flow in these kind of geometries, where you have length scale in one direction or y direction, which is h naught, and length scale in x direction, which is L, and they are quite different. They are different in the sense that if you define this epsilon as h naught by L, then this is much less than 1. Then in this limit of epsilon, what are the governing equations we were looking at? So, when we non-dimensionalized, we said okay, the scale of x velocity is some u naught, the scale of y velocity is some v naught, the scale of x is L, the scale of y is h naught. And then from the continuity equation, we concluded that del u star over del x star plus del v star over del y star equals 0, because v naught was related to u naught as this. Okay. So, we said that any y direction velocity is actually due to the deflection of the walls. If these walls were straight, there would not be any y direction velocity. So, if you have some x direction velocity which is u naught, okay, and the flow direction is very close to the wall, let us say the flow direction is in the direction of the walls, then you can say that v naught by u naught is approximately h naught by L. That was our idea of deriving this scale of y direction velocity, and from here we concluded that there is no epsilon that remains even in your dimensionless continuity equation. And then we had derived the dimensionless y momentum equation, and to derive that we had used that the pressure scale is something mu u naught over mu u naught L over h naught square. So, this pressure scale we had derived by saying that pressure differential is balancing the viscous forces. So, if you have mu u naught by h, okay, if you have mu u naught by h as the viscous stress by h naught as the viscous stress, and then you multiply it with L, okay, this is the force per unit depth on a fluid volume. This should be equal to P naught into H naught, and from here you can get this pressure scale instead of P, yeah, P naught we can write. So, this is our P naught, okay, or the pressure scale, and once we had written this, we had written the dimensionless y momentum equation, which was epsilon cube times R E H u star del v star over del x star plus v star del v star over del y star equals minus del p star over del y star plus epsilon square del 2 there was another epsilon square here, okay, and from here we concluded that at order 1 any term which is not multiplied by epsilon, which is what we call as order 1, we said that at order 1 del p star over del y star is 0. And then we had derived the x momentum equation similarly, which gave us epsilon REH times u star del u star over del x star plus v star del u star over del y star equals minus del p star over del x star plus del 2 u star over del y star square plus epsilon square. Okay. And then at order 1 or at leading order, we said that the equation satisfies simply this guy. But remember that even though the equation looks similar to your unidirectional flow in a channel, this velocity u star is not anymore just a function of y. Okay, this is not a unidirectional flow. Okay, this is not a unidirectional flow. You have y velocity component in this flow. Okay, it is small, but it is there. Okay, in this analysis, it is small, but it is there. So del star del 2 u star by del y square equals this. Even though you can write this as dp star over dx star, because pressure is not a function of x at leading order, but it can be a function of x, which means that the argument that you usually give, this is just a function of x, this is just a function of y, so they are constant, that does not hold anymore. Actually pressure can have a non-linear variation in x, and that is what we had derived using the continuity equation. So if you solve this equation, you will get that u star is equal to, so the boundary conditions will be that let us say we define in h star, which is h of x over h naught, and the boundary conditions are that u star at plus minus h star by 2 is 0. So once you substitute these boundary conditions, we get the solution of u star as a function of y star. There is x also. So we have 1 by 2 dp star over dx star uh, y star square plus C1 x y star plus C2 x. Remember, these were constants when we solved for this flow in a channel, straight channel, but when you integrate this, basically any constant that you will add is basically a constant in y only. Okay, it is not a constant in general, it is a constant only with respect to y. So we will add C1 x and C2 x, which we say they are functions of x. And now when we substitute the boundary conditions, so we will substitute these boundary conditions, and so we will obtain that u star should be minus h star square over 8 dp star over dx star 1 minus y star square over h star by 2 square. Okay. So this is what we will obtain. Again, we have derived C1 and C2 using these two boundary conditions. Okay. And since h star is a function of x, remember h star is a function of x. So this does not mean you have a simple parabolic profile, same parabolic profile at every x location. You will have different parabolic profiles at different x locations. Okay. And now when you substitute this in your continuity equation, so you can substitute, actually you do not even need to substitute in your continuity equation for now. You can just say, okay, if I am calculating this guy minus h star by 2 to h star by 2. So this is your flow rate, let us say q star per unit depth. Okay, it is all dimensionless flow rate per unit depth. So if you calculate this, you will obtain that it is minus h star cube over 12 dp star over dx star. Okay. And from here we said that for a given flow rate, remember this flow rate, we want some constant flow rate throughout the, channel, right. Is this, can this flow rate change in x? Can this flow rate change in x? Can the flow rate change in x? Why? Why can't it change in x? Why can't the flow rate change in x? Let us say if I ask you to compute from this equation. So, y has been integrated out. So, if it is a function, it will only be a function of x. So, if I ask you to calculate this guy, how will you calculate this? How will you show that dq star by dx star is 0? Huh? Mass conservation. Okay, you are qualitatively right, but how will you show it mathematically from here? Dq star by dx star equals 0. Can we show that? So, you can differentiate this, and what we can write is this is del u star over del x star dy star from minus h star by 2 to h star by 2. So, just apply the Leibniz theorem, okay, times h star by 2 minus u star minus h star by 2 times h star by 2 with a minus sign. What is u star at h star by 2? 0. What is this guy? So, you are left with this, and from continuity equation this is equal to minus h star by 2 to h star by 2 del v star over del y star dy star, which is nothing but v star at h star by 2 minus v star at minus h star by 2. What about v star at h star by 2 and minus h star by 2? 0. Okay. All velocities are 0, these are hard walls, we have no slip as well as no penetration. So, dq star by dx star is 0, okay. And the qualitative information that mass conservation requires that the flow rate does not change in x was used here when I substituted del u star by del x star through continuity equation. Continuity equation is another way of saying mass conservation, right. So, this is indeed through mass conservation, but you have to show it like this. Okay. So, q star is not a function of x, it can't be a function of y, we have already integrated y out. Okay. So, that means you can write that dp star over dx star is equal to minus 12 q star over h star cube. Okay. And from here you should understand that when h star is constant, which was the straight channel example, then your dp star by dx star, which is the pressure gradient, is constant. But if your h is varying in x, then you have a variation in pressure, non constant variation, non-linear variation in pressure. dp star by dx star is not constant. Okay. And this relation also gives you, so for example, if you have a channel of length capital L, let us say there is some length capital L, if you integrate this out, you can get that P2 star minus P1 star, let us say this is P2. So, you can get what is the pressure differential you need to maintain to have some flow rate. What is the pressure differential you need to have some flow rate. Okay. Of course, P2 has to be less than P1 to maintain a flow rate in this direction, in the x direction, right. So, that is why there is a minus sign there. Okay. So, this is the crux of lubrication theory, and where is this used, where is this practically used is, so we will give an example of its practical usage, and that comes in a so that comes useful, that becomes useful in tribology. For example, tribology is the study of bearings and lubrication. So, let us say you have something like a shaft. Okay. Let us say you have a shaft which is inside a housing. Okay. Let us say the shaft is supposed to rotate and it is inside a housing. Then you will maintain a thin gap between the housing and the shaft, and you will put some oil or lubrication grease inside. And when the shaft rotates, the flow between the shaft and the housing will obey all the fundamentals that we discussed so far. Okay. This is the example of the so called journal bearing. It's called a journal bearing. Okay. The other examples are, let us say you have a again you have a shaft which is rotating, but you need to support it against some thrust. Okay. For example, let us say you have a jet engine, you have a shaft which is connecting the turbine and the compressor blades, and due to the turbine and compressor, so if it is exerting a forward thrust, then the shaft will be experiencing a negative thrust. Okay. If it is pushing air outside, then shaft will be, so if the plane is moving like this, then shaft will be experiencing a thrust like this, right. So, how do you make sure that it maintains a smooth contact, it is able to rotate and also sustain this thrust. So, these are called thrust bearings. Okay. Where, so in these bearings you have an axial load that you are trying to sustain. In these bearings usually you have a transverse load that the shaft is trying to sustain. So, in journal bearing the example is something like this, you have a shaft and this is your housing, and then there may be some weight or some other loading transverse to the axis, and that is required to be sustained in this journal bearing case. These are thrust bearing cases. So, all of these examples you have slipper pad bearings also, okay, where the idea is you have something like this in a rectilinear motion. So, maybe this is moving or this is moving, and this is a very thin gap, and you are required to maintain sufficient lubrication to prevent mechanical wear and tear. Basically, everywhere you put the lubrication oil or grease to prevent mechanical wear and tear, and the flow of the lubrication oil or grease that you put obeys the theory that we have just discussed. Okay. There is one more complication than compared to what we have discussed, and that is that in these cases, so for example, let us say this is moving ahead, then you have some velocity of the walls as well. What we just discovered was flow through thin slots where the walls were not moving. The walls can be moving also. Okay. And in that case, the equation that needs to be derived, technically the equation that you should be able to obtain is what is the thrust or what is the pressure or what is the force that this lubrication flow can sustain. Okay. Basically, you should be able to compute the pressure inside the flow and the viscous stresses due to the flow. So, those can be computed by what is called the Reynolds equation, which we will derive now. Okay. We will consider a setup very similar to this. Okay. We have some h of x here, okay, and we will say that the bottom surface is moving with some velocity u naught and the top surface is moving vertically up with some velocity v naught. Okay. And what we are required to obtain is what is the pressure distribution inside this flow. Okay. There is rho comma mu, and all the lubrication assumptions hold. So, epsilon, which is some h naught over L, is much less than 1, and the other one was that epsilon times REH should also be much less than 1, is also much less than 1. So, these two conditions hold, and within these two conditions, how can we determine the pressure inside this flow? So, to derive this equation, we write the dimensional version of our lubrication equations. So, we have x, y and z. We are going to consider a 3-dimensional situation now, and the governing equations that we will have within lubrication approximation. So, within lubrication approximation, basically at leading order. Okay, we are looking at leading order equations. We will have del p over del y as 0, we will have del p over del x as mu del 2 u over del y square, and we will have del p over del z equals mu del 2 w over del y square, where w is the velocity in z direction. So, we have u, we have v, and we have w. Okay, so, this is a 3-dimensional situation where this what I have drawn is actually a plate which is extending outside the board. And of course, we will have the continuity equation del u by del x plus del v by del y plus del w over del z equals 0. Okay. We'll have the boundary conditions from here. So, for x velocity u, we have that equals 0, or rather equals u naught, and u at x comma y equals h of x is equal to 0, and for w we have it 0 both on both the walls. Notice that we have PDEs in y only, so we have the y boundary conditions only for now. We need them only, we need only those for now to solve these equations. So, we will get for velocity as 1 by 2 mu del p over del x. So, this is something that we have already solved for with this kind of set of boundary conditions and this equation, which was the linear combination of Couette flow and Poiseuille flow. So, we have y square minus y h plus u naught 1 minus y by h. Okay. And then w will simply have 1 by 2 mu del p over del z times y square minus y h. Okay. Is everyone okay with this solution? If you have questions, please ask. You can just integrate this, have the two constants, use these boundary conditions to solve those two constants. It is very straightforward. Same thing here.
So I cannot understand how is there a z component of velocity here.
There may be del p by del z, no, pressure could be varying in z, so that will give us a z component of velocity. We are entertaining the full 3-dimensional situation.
But why is there not a v? Sure. Del p
V
by del
is
z.
small because this h by L, we are within lubrication approximation. Okay, so this is a situation like something like this, let us say, if you are facing issues in visualization, then this is a situation like this. Okay, there are two plates with very narrow gap in between, but that gap is not constant. It could, the gap could be a function of x and z also, by the way, but for now I am just entertaining it to be a function of x only. Okay, and this is what we get. And now to you should understand that these things are not known. Okay, these are unknowns. We still have to find them. These are unknowns. We still have to find them. And the way we find del p by del x or del p by del z or an equation that governs this is through the continuity equation, using the same procedure that we just followed to show flow rate is constant. So, what we will say is that del v by del y is minus del u by del x minus del w by del z, and I will integrate this equation from 0 to h. To be specific, this is 0 to h as a function of x. Okay. So, what is del v by del y? dy from 0 to h, it is simply v at h minus v at 0. Okay. It is simply v at h minus v at 0, and then the right hand side is minus del u by del x dy 0 to h minus del w by del z dy 0 to h. So, we know that this thing, if I write it like this, then it is simply u integral del u del x dy 0 to h minus u at h into, actually there it should have been h prime, just fix this in your derivation when we showed that dq star over dx star is 0. Okay. I think I did not write h prime, I wrote h. So, when you integrate it from minus h star by 2 to h star by 2, this guy, okay, this should be del u star over del x star dy star plus u star at h star by 2. It does not impact the result, but just to be, okay, it should be this, not h star by 2, and then the minus sign thing. Okay. So, here we will have dh over dx. Huh?
So you didn't write the differential there.
But it should be there, no?
Okay.
It should be there. The differential should be there. That is why I am asking you to correct it in your notes. Okay. So, and then we have minus u of 0 times 0. Okay. We know that u of h in our situation is also 0. So, basically if I have del u by del x dy, I can pull the differential out safely. Okay. In this particular case, we can pull the differential out safely, and I can write that del u by del x dy as simply del by del x of u dy. What is u dy? What is u dy? Can we calculate it from here? So, it will be 1 by 2 mu del p over del x y square minus y h plus u naught 1 minus y by h. So, what is this? What is this? Can someone simplify? This is 0 to h, sorry. So, 1 by 2 mu del p over del x. What is the integral of this? So, we have y cube by 3 minus y square h by 2. So, h cube by 3 minus h square by 2, which gives us minus h cube by 6. And from here what do we get? We have y minus y square by 2 h. So, h minus h by 2. So, u naught h by 2, which is basically minus 1 by 12 mu del 2 p over del x square, or no, hold on, del by del x of h cube del p by del x plus u naught by 2 dh over dx. Okay. This is what we get for this term del u by del x dy. Similarly, we can compute del w by del z dy. Even if your h was varying in z, you could pull the differential out of integral safely. Even if h was function of z, you could pull it out safely because w at h is 0. Okay. So, it will not affect your Leibniz formula. So, this can be written in this particular case as this, and from the solution of w, as some of you may have already guessed, the solution is del by del z minus 1 by 12 mu del by del z h cube del p over del z. this should be del h over del x, not dh over dx. Okay. Because if you really look at it, h is not just a function of x, it is a function of t time also in this case. If you have a v naught, okay, if you didn't, even if you didn't have any v naught, you had some u naught, then h at a particular location could change. Let us say this slanted wall was moving in x direction, even then h as a at a particular x location would change. Okay. So, in this particular case you have to say that h is a function of x and t. Okay. And what is del h over del t, by the way? So, del h over del t, that is variation of h at a particular x location, what is it equal to in time? V naught, right, simply V naught, or V at h equals V at y equals h, which is V at y equals h, which is this guy. There is a minus here also, minus 1 by 12. So, now substituting this there, we get 1 by 12 mu of del by del x h cube del p over del x plus del by del z h cube del p over del z So, there is a minus which will become plus equals u naught over 2 del h over del x, and then v at h can be written as del h over del t plus del h over del t. Okay. And this is your Reynolds equation. This is in many textbooks you will see this is your Reynolds equation for pressure inside this kind of a flow, or flow caused by this kind of a variation in the wall velocities and within the lubrication approximation. As you will notice, this is a second order PDE for pressure in x and z. So, that means to solve for the full pressure variation, you need two boundary conditions in x, two boundary conditions in z. Okay. So, in this kind of a case, let us say this is your, these are your boundaries. So, on this face what is the pressure, on this face what is the pressure, that will give you x boundary conditions, the two x boundary conditions, and on this the face behind and the face at in front, what are the pressure values, that will give you the other two boundary conditions in z. Okay. And then you could solve for the pressure variation. Of course, you need to solve for that pressure variation, you need the information of the geometry, which is this del h over del x. Okay. There is a very nice daily example that you guys must have experienced yourself as well, which we can physically reason from this equation. So, let us for a moment assume that there is no z variation. Okay. Let us for a moment assume that it is a 2D situation, and in 2D we have 1 by 12 mu del by del x of h cube del p over del x equals u naught by 2 del h over del x plus del h over del t. And let us say what we are trying to do is we are trying to lift something which is not flat. Okay. We are trying to lift something which is not flat and has some viscous fluid between itself and the bottom surface. So, most of you must have experienced this when you are trying to pick up a tumbler or something in your kitchen from a wet surface, it sticks. You try to pick it up, it sticks, right. And we will show that basically the sticking is due to the motion that you are giving it in the vertical direction. It causes a flow here which reduces the pressure compared to atmospheric pressure. So, it is the atmospheric pressure that is trying to pull that push that utensil down, and you are trying to do the work against that atmospheric pressure. Okay. So, let us assume that the variation is linear. Okay. Let us say the variation is linear, and or even not linear, let us even do it for a constant variation. Okay. Let us do it for a constant h. So, let us say h is constant. So, del h over del x is 0. Okay. H is some h naught. So, we have h naught cube by 12 mu del 2 p over del x square equals. So, you are just trying to give it vertical velocity, the top surface, which is del h over del t, which is nothing but v naught. Okay. You are just giving it that velocity. So, when you solve for this, everything is a constant, it is very easy to solve. So, you have del p over del x as 12 mu over h naught cube v naught times x. Okay. You can say that it is some plus c, but if this is your x equal to 0, okay, this is x equal to 0, and for a symmetric variation of pressure, you will say that del p over del x at x equal to 0 should be 0, which means c is 0. Okay. This is the symmetric boundary condition. So, you will have del p over del x as simply 12 mu v naught x over h naught cube, and from here we will see that pressure, or let us integrate it in x, let us integrate it uh, from x to L by 2. Okay. This, let us say this is L, this is L by 2, and the pressure outside is some P atm. So, this becomes P at L by 2 minus P at x equals 12 mu v naught over h naught cube L by 2 square, there is a 2, there is another 2 that will come, minus x square. Okay. So, when x is less than L by 2, what is, how does P x compare to P at L by 2, which is equal to P atm? When x is less than L by 2, P x is less than P atm, right. So, P x is less than P atm. Okay. So, you have a, as you try to pull this plate up, you are basically reducing the pressure due to the flow that is caused by your action of pulling the plate up, and that flow is reducing the pressure compared to atmospheric pressure, and it is then when you do the force balance on whatever body you have at the top, you will have a net force in the vertically downward direction. Okay. And that is what is trying to keep the body there, and this is basically called viscous adhesion. It is technically not adhesion. If there was no atmosphere or there was no gravity, then nothing will happen. This is not purely viscous adhesion, but you are experiencing this because of viscous flow inside. Remember, all of this thing was there due to viscous flow. If there was no viscosity, nothing will happen here. Okay. So, the opposite of this, when you are trying to push something, okay, when this V naught is negative, when you are trying to push something, this will also create a flow. Usually that flow is called a squeeze film flow, okay, which the name is kind of self explanatory. You are squeezing a film of fluid that is flowing as a result of this squeezing action. Notice that when x is less than L by 2, P x is less than P atm if V naught is positive. Okay. I mean, I assume that V naught is positive, V naught could be negative as well, then the case would be reversed. Okay. If you are trying to push something down, then V naught is negative, P of x will be greater than P atm. Okay. So, the pressure does not always fall below atmospheric. It falls below atmospheric when you are trying to pull it up. If you are trying to push it down, then the pressure is increasing compared to atmospheric pressure. Any questions? Do we have any questions? So, there is a cylindrical analog of whatever we have discussed for Reynolds equation. There is a cylindrical analog also. I will not solve it in the class, but I will give it to you in the notes, and that is the analog of that journal bearing that we had drawn, and the analog problem goes something like this. So, you have a cylinder that is rotating. So, let us say the cylinder is rotating with it has a radius r, it is rotating with some omega 1. Okay. And then the analog problem is that you have another outer cylinder which is offset from this guy. Okay. This guy has a center here at the origin, and the center of the outer cylinder is somewhere here, and the radius of this outer cylinder is 1 plus epsilon times r, and this guy is rotating with an angular velocity omega 2. Okay. And this offset between the two centers, the offset between the two centers you can write as epsilon r times some lambda, where lambda is some another fraction. Okay. It may be order 1, it may be very smaller, much smaller than 1 or something. Okay. And so, notice that I have a 1 plus epsilon r. So, the radius of the outer cylinder is just slightly higher than the radius of the inner cylinder. So, the gap between them is small, and you can expect that all the lubrication approximations that we have covered just now, when the transverse length is much smaller than the streamwise length, okay, they will hold, and you can derive. So, you can apply the Navier-Stokes equations in cylindrical coordinates. Okay. You can apply them in the cylindrical coordinates and solve for this problem very similarly to what we have done in Cartesian. Okay. The only thing that you will have to be careful is that if you are applying it in cylindrical coordinates, notice that these are your unit vectors. This is e hat theta, this is e hat r. Okay. The surface of this outer cylinder is not at a constant radius. With respect to your origin, the surface of your outer cylinder is not at a constant radius. If you look at this distance r, then it is changing with theta. This distance r will be changing with theta, right. You can compute that distance. So, this is 1 plus epsilon r, this is epsilon lambda r. So, essentially, and this angle between them is always theta. So, it will be 1 plus, so r times 1 plus epsilon r square 1 plus epsilon square plus epsilon r lambda whole square minus 2 r 1 plus epsilon r lambda cos theta. This is what your r of theta is. Okay, be careful with that. Plus, no, there will be plus here. Okay, so you have to be careful when you are looking at the, basically when you apply the boundary conditions, then in that case you will have that u dot n at the outer surface. So, outer cylinder surface will be 0, and u dot t again at the outer surface, where this t is the tangential vector, unit vector, will be equal to omega 2 times r 1 plus epsilon. The rotation of outer cylinder is about its own center, it is not about the origin. So, it is not omega 2 times r theta, it is omega 2 times its radius only. Okay. The rotation of cylinders is about their respective centers only. So, this is the only place where you will have to be careful and you will have to derive what is this n hat t hat using this r theta. Again, if you have a surface defined, you can find its normal and tangent by taking the gradient. So, you have to do that carefully and then you can follow the whole procedure that we have just covered for Cartesian coordinates. Okay. So, with this we are going to, we are actually approaching the end of low Reynolds number flows. Okay. We are approaching the end of low Reynolds number flows, our discussion of low Reynolds number flows. And so, to just summarize that, what we have covered in low Reynolds number flows is we started with the non dimensionalization, we looked at the dimensionless Navier-Stokes equation, we applied R e much less than 1 condition, and then we saw that basically viscous stresses and pressure have to balance each other out in the governing equation. Okay. Viscous stresses and pressure have to balance each other out, and once you derive that, we followed flow past a cylinder, flow past a sphere. Okay. You can solve for, so probably you have seen this in your practice sheets, you can do the solution in these kind of scenarios as well. Let us say you have some angle alpha, you have two plates and there is flow coming in and going out. Okay. You can solve the Stokes flow equations in cylindrical coordinates in this example. Okay. You could have a situation where you have two plates, let us say, and they are hinged. Okay. And they are hinged such that they are moving towards each other and there is viscous fluid between them. Okay. So, in this is like a cylindrical analog of your squeeze film. Okay. You are trying to close the gap on this liquid, and as a result of that you will be squeezing some flow out, and in the limit of low Reynolds number you can solve for that kind of a flow as well. Okay. Then we will move to lubrication theory, where you may have two different length scales to define a Reynolds number, and we saw what are the limits under which lubrication examples can be solved. Low Reynolds number flow is a field of itself. Okay. If you move to more advanced studies, then you will see there are dedicated courses for low Reynolds number flows. For example, swimming of microorganisms in a liquid, in a fluid, is an example of a low Reynolds number flow. Okay. Particles in a suspension that are settling down, sedimentation that you guys probably have experienced yourself, is an example of a low Reynolds number flow. Okay. So, a lot of biological examples are there, a lot of environmental examples are there where low Reynolds number flow equations are applicable. Okay. So, it is not like this is just some theory on the board, they do find application. For example, actually one of your problems in your midterm, the third problem, that was a part of Einstein's thesis when he tried to calculate what is the viscosity, effective viscosity of a suspension which has dispersed spherical particles. Okay. He used that extensional flow, he derived the extensional flow solution and derived what is the effective viscosity of a suspension. Of a normal fluid you have, if it is mu, then if you disperse some very small cylindrical spherical particles in that fluid, then what is the effective viscosity of that. Okay. So, these things find applications almost everywhere. Okay. But the other side of the coin, which is, let us say, high Reynolds number flows, or so moderate Reynolds number flows are not really very interesting, because if you remember our governing equation, the dimensionless governing equation, which was, let us write it in a very short form. Okay. If you remember our dimensionless momentum equation Moderate Reynolds number flows are not really very interesting, because you see then we cannot really apply any simplifications, we cannot do any approximation business, because if your Reynolds number is moderate, then all terms are in a way balanced important in the equation. Okay. Then you are stuck with basically solving the full nonlinear equation, which is, I mean, okay, that was the whole problem that we started with. So, that is why you will find very less discussion on moderate Reynolds number flows, because there are no further simplifications that you can make. Okay. Once you say that your Reynolds number is neither too large nor too small, okay, then that means all terms are equally important, then basically you are stuck with solving Navier-Stokes equation. Okay. So, that is why moderate Reynolds number flows are not really that interesting to us. We have covered the low Reynolds number flows. The next discussion of most of this course is going to be on the so called high Reynolds number flows or high RE flows. Okay. But there is a catch there. Okay. When we applied low Reynolds number approximations or simplifications to low Reynolds number flows, we were in a way naive. We were naive because what we said is, oh, RE is much less much less than 1. Let us just multiply this whole damn equation with RE and ignore the terms which have RE and keep the terms which do not have RE. Okay. But now when you have high RE flows, then we fall into some paradoxes, and one of the paradox that you can see from here, let us say you have high RE flows. So, 1 by RE is going to be some epsilon which is much less than 1. So, your dimensionless Navier-Stokes equation will read something like this. Okay. And then maybe those who have learned something in your low Reynolds number flows will say, oh, epsilon is much less than 1 if your non dimensionalization is correct, whatever is not, whatever does not have epsilon. So, this del square u should be of order 1. So, if these terms are order 1, this order 1 multiplied with epsilon is smaller order. So, just throw it out. So, at first order the governing equation you will write is this. Okay. Basically what you will say is, oh, Reynolds number is very small, Reynolds number was inertial forces by viscous forces or large, Reynolds number is large. So, inertial forces by viscous forces is large. So, means viscous forces are almost negligible, no. So, let us just throw them out, let us just throw them out of the governing equations. Okay. So, let us throw out the viscous stresses, but what happens when you throw them out? If you look at it mathematically, we will look at it physically also, but if you look at mathematically, what happens when you throw them out is that you reduce the order of PDEs. They are no longer, if you ignore the viscous terms, they are no longer second order PDEs in each direction, these are first order PDEs in each direction. What is the result of that? You just reduced an order of PDE. So, if you had the full Navier-Stokes equation, you said it is a second order equation in x and y and z, you needed 2 boundary condition in x, y and z, but now you cannot satisfy both the boundary conditions in x, y and z, because your order of PD is not second anymore. Okay. So, intuitively you can think about it as an example of solving this equation. What happened here, if I say, what happens here if I say epsilon is much less than 1 and you just drop epsilon term naively, then you are left with this, x equals half is the solution. But calculate the solution from the full equation. So, apply your quadratic knowledge, and so what is the solution of this equation? What is the solution of this equation? 2 plus minus 4 minus over 2 epsilon. So, if you cancel things out, what do you get? 1 plus minus square root 1 minus epsilon over epsilon. I can write this I can write that as 1 by epsilon plus minus square root 1 minus epsilon by epsilon. Now, in the limit epsilon tends to 0, what are these two values? What are these two values in the limit epsilon tends to 0? Are both of them infinity? So, in the limit epsilon tends to 0, let me write this using binomial expansion. I can write 1 minus epsilon 1 by 2 plus epsilon square by 4 and things like that over epsilon. So, what do I get? So, one root that I get is 1 by epsilon minus 1 by epsilon plus half minus epsilon by 4 and so on. These things cancel out and you get half minus epsilon by 4 plus higher powers of epsilon. That is one root that I get. What is the other root? What is the other root? We have epsilon plus 1 by epsilon minus half plus epsilon by 4 and so on, which is what? 2 by epsilon minus half plus epsilon by 4. We completely missed out on this solution, the 2 by epsilon solution, when we just dropped this epsilon square term. We got a first order approximation of this solution, which is half minus epsilon by 4. We simply dropped epsilon, so we did not have any epsilon in our solution, we obtained half. Okay. But we completely lost this solution. You when you dropped epsilon square term, you converted this quadratic equation into a linear equation. Okay. This is a solution of this equation, but you are completely oblivious of that. Okay. So, one has to be very careful when there is a small parameter that is multiplying the highest order or highest degree term in your equation. If it is a differential equation, then you have to be careful if it is multiplying the highest degree highest order equation. If it is an algebraic equation, then you have to be careful if it is multiplying the highest degree equation degree term, which is what you saw here. Okay. And this is the beginning of our discussion on high Reynolds number flows, and as we will see that the so called potential flows or inviscid flows, they are not the same, and the boundary layer theory are the two sides of the same coin of high Reynolds number flows. Okay. One is a naive substitution of epsilon of ignoring epsilon terms. One is the naive substitution of, okay, throw these epsilon del square u out. The other one is a careful assessment, is this del square u indeed order 1, because as it happens that this del square u, when you non dimensionalize, notice when you non dimensionalize this equation, the x and y and z length scales were all same. As it happens, this del square u can be much larger than 1 if you have some boundaries. If you have solid boundary, then very close to the boundary you can have del square u much larger than 1, which is multiplying a very small number, and the multiplication can be finite, and you cannot just naively drop out every viscous stress term, and that is the whole point of boundary layer theory. Okay. So, you get a part of the solution from potential or inviscid flows, which is something like this. Okay. You get the other part of the solution from boundary layer theory. Okay. So, we will continue from here in the next lecture.